Hi, and welcome to Module 8 of Lecture 5. In this module, we're going to present the very last of the rules for integration by parts. Now, this rule tends to drive fear into people, but honestly, it's relatively straightforward once you connect it to its analog rule in differentiation, the product rule. So rather than present the rule first, because it looks kind of long by itself, we're going to derive it first and show exactly how relatively straightforward it actually is. So, remember the product rule for differentiation. It looks like this. F times g, where both f and g are functions of x. That derivative is equal to f prime g plus fg prime. Right? There's the product rule. Okay, we derived that back in the previous lecture for derivatives to understand how to take the derivative of a function of a product, a function of a product of two smaller functions. Now, here's what we have here. Let's integrate both sides. Okay, first step. Second step, the integral is linear, so this right-hand side equals the integral of f prime g plus dx plus the integral of fg prime dx. Right? Now the integral on the left, right, by the fact that the integral is the inverse operation to the derivative, the integral of a derivative will return the function back again. There's going to be a constant here, but we're going to ignore that for the sake of this because the constants will be in all the aspects. So you get fg back again. And that's pretty much the entire thing already. We rearrange, and we put this on one side, so that's this term, and that's going to equal fg minus f prime g dx. And there is the integration by parts rule right there. That was it. It comes directly from the product rule in differentiation. It's used in exactly the same scenarios when you have a product of two functions and you want to integrate them, and you can't integrate them as a whole. What you can do is use the integration by parts rule to try to integrate them, treating each individual piece of the larger function as its own function, just like in differentiation. Now this integration, so it's going to have a little twist to it. In differentiation, you can always pick two things and use the product rule to split them up, and that'll work out for you every time. Integration, not so much. There's, however, a pattern to this. So note that on the left, you've defined it in a very particular way. You defined one function as f and one function as g prime. On the right, you have f and f prime and g. It means two things. One, your best benefit for f is going to be to use an f that's going to get less complicated when you differentiated it, right? So over here, f stays the same over here, but in the new integral you have to calculate, f becomes f prime. So if you can get something that simplifies, then this new integral might be easier than the old one. However, point two, on the left-hand side you had g prime. You're going to integrate that to get g and g over here. So you want g prime to be something that does not integrate to something more complicated. Because the whole point of using integration by parts is to basically switch which is the complicated function. You have an f and a g prime. If, say, g prime is some kind of function that stays pretty close to the same when you integrate, like, say, an exponential, whereas f is something that gets simpler when you integrate, like, say, x, then it's convenient to call xf and call e g prime, and you integrate g prime, you get g, it stays the same, so it's e to the x over here, whereas when you differentiate x, it goes away, and suddenly this integral becomes manageable. I'll give you the example explicitly in a second, but that's the idea. The idea is you have you split up your function into two parts, f and g prime. And again, don't worry the fact that we have a g prime there, it's just a function. It's the derivative of g. Whether we call it g prime or q, it doesn't make much of a difference. It's just sort of a marker. The important part is the first function, the f here, you're going to differentiate. And the second function, the g prime, you're going to integrate. And you're going to try again to solve that integral over here. I think I'm making blue. You can try again to solve that integral over there on the right, but now with the roles flipped. F became f prime, but g prime became g. If that integral is solvable, then you've managed to use integration by parts to fix your original integral, integrate the whole thing out. If that integral is not solvable, you gain nothing by this process, and there's very little point. That's not entirely true. There's some examples you can get, particularly when you have trigonometric functions, where you can do this process twice and then manage to get nothing either time individually, but put them together and get somewhere. Not very common for political science applications, so we won't talk about that too much. By and large, if you're not getting anywhere in the first iteration here, you don't need to use this. Now I did mention bounds here. Bounds are just fine. If you put an a and a b over here, the same bounds exist over here. The only complication is this thing you integrated out, and this thing should be evaluated at a and b. Remember, the vertical line means evaluated at b, evaluated at a, and subtract the latter from the former. Subtract the second from the first. Okay. So this is with bounds. That's the rule. So now I'm just going to practice the rule a couple times. This rule, again, much like the chain rule, involves more complexity theoretically as compared to the product rule or the linear rule. Integration by parts has less theoretical complexity than substitution does. Substitution is more complex theoretically than both by parts and linear. So this should be relatively straightforward, even though people tend to make it into a big thing, because the rule itself looks long, right? And you often see variations of this, like this, integral of u dv equals uv minus the integral of v du. This has the benefit of having fewer primes, and treating this as a differential by itself. But again, this one they've boxed out here is more familiar to us given what we've done so far. So we're going to stick with that one. But if you see this, it's the same thing. You just make g prime dx dv. And you make f prime dx du. Why do you do that? To change the variables. It's the exact same logic we used in the previous module. At the very end, we discussed a different way of looking at substitution when we converted from x to u. Then we had a g prime in there. Same exact thing. There's no difference. So if that makes it work for you, right? Remember we had du equals g prime dx. Same logic here, right? G prime dx, you convert to du. Here, g prime dx becomes dv. Same exact thing. But again, we're going to stick with the boxed equation here. Okay. So that's the rule. Now it's time for an example. We'll do a few of them to get a handle on this. Okay. So first, the one I talked through too quickly over here. X e to the x dx. And the first thing here is to note why we're using integration by parts. Well, first we check linearity. There's no sums, no differences. Not helpful there. Next, we check to see if there's some kind of function composition. There's not here, right? E to the x is as small as it gets, right? It's an exponential function by itself. Same with x. There's no composition at all. There's nothing to substitute into. That leaves by parts. Integration by parts is sort of the rule of last resort. If the other two ones don't work, they're more specialized, you can try by parts. If by parts doesn't work, either you messed up or it's not integrable. One of the problems with integration is you can't always tell if you messed up or if it's not integrable, meaning there's no integral possible given the method you're using. So you just have to try. So here's integration by parts. We're going to try to define what f is. Now here we have two choices, right? We can make e to the x f and x g prime, but that would involve integrating x, which would create 1/2 x squared, if you remember the rule for powers. and differentiating e gets us nothing because it stays e. So the new integral we have on the right would even be more complicated than the old one. So let's just write that out. If we had set f equal to e to the x and g prime equal to x, then we'd get that this thing equals 1/2 x squared e to the x, that's the fg part, minus the integral of 1/2 x squared e to the x dx, and we're actually in a worse shape than we started with, right? We have an x squared e to the x, and we can't solve that either. So this gets us nothing. So this is a bad idea. So instead, we're going to try this again, but now what we're going to do is make f equal to x and g prime equal to e to the x. And again, the reason we do that right off the bat is we note that we're going to differentiate x. The derivative of x is 1, so that'll go away completely, making our function simpler. Making our integral simpler, rather. Whereas g prime integrates easily to e to the x again, so nothing changes. So now we can do this, and we get this integral here, the integral of f g prime dx equals fg minus the integral of g f prime dx. That's integration by parts. This is the one up here, the same one. So that's going to equal f, which is this. The integral of e to the x is e to the x. Now we're going to subtract. The integral of g is e to the x. F prime is 1. So that goes away, and dx. Now, we can actually integrate the last one, which is just e to the x again. So now we have x, e to the x, minus e to the x. And there you go. That's the integral of x e to the x. You can even simplify if you wanted to. X minus 1 e to the x. It's great. And there's a c here at the very end. I mentioned don't put the c in the beginning because the c's will pop up eventually anyway. So there should be a c here. Once you finish off with integrals, stick a c at the end of it. If you have definite integrals, don't stick a c at the end of it. That's pretty much it. There you go. There's the integral of x e to the x using integration by parts. You don't have to use it. I said oftentimes you use this once if it works out. Sometimes there'll be more than once necessary. Let's do a really quick example of that. Let's try x squared e to the x dx. Now, we've already gone through our mistake of putting the wrong f and g, so let's stick to f equals x squared and g prime equals e to the x. Therefore, f prime equals 2x and g equals e to the x. It helps sometimes to write this out. So now the first term is f times g. That's x squared e to the x. The next term is the integral of f prime times g dx. Okay. Now the first term is done. It's simplified. The second term we still can integrate. Now we just actually did that integral, so I'm going to skip a step here. Right. We get minus 2 times the exact same integral we just did. If you recall from the previous slide, or not the slide, the previous screen, that integral was x minus 1 ex. So by using integration by parts twice, we get our answer, and we can put them all together and get x squared minus 2x plus 1 times e to the x is the integral of x squared e to the x. And we can keep doing this over and over and over again, getting more and more longer and longer polynomials multiplying e to the x, but it's always possible to do. Now you might ask why we care about this kind of thing. Well, this kind of integral is how you would take an expected value in what's called an exponential probability distribution function. But that's how you would do it. You can do more complicated examples if you want. There'll be some more examples in the problem sets, but that's all it is. Identify f, identify g prime, try Try to pick your f such that it gets simpler when you differentiate. Try to pick your g prime such that it gets not much more complicated when you integrate, and you're done. Now you might again be saying, okay, look, you've given me two straight examples of nothing but exponentials, right? This is all it's used for. In political science, mostly, but you can do a couple more things. So I'll try one more example just to show you that it's not only exponentials. So let's say you had some kind of thing like, let's say, x plus, try to figure out a good example here. Okay, there we go. Let's say you had x over x plus 1 to the 1/2. So this is pretty messy. It's not obvious. Well, you could rewrite it though. This thing is going to be the integral of x times x plus 1 to the negative 1/2 dx. As it is, we can't do anything with it, but we have two things multiplying each other. Each of these by themselves can be integrated. So we can deal with this. Let's again make f equal to x, so that f prime is equal to 1, so we get rid of that. And let's make g prime equal to x plus 1 to the negative 1/2. Now we need g here, right? Now, it turns out that it's a really easy substitution because this is a composite function. It's 1 over the square root of x composed with x plus 1. But since the derivative of x plus 1 is just 1, the composite function is not very interesting, so we can pretty much ignore it. So what we're going to do is show that g is equal to the integral of that. So you add 1 to the negative 1/2, gives you positive 1/2. 1 over positive 1/2 is 2. So this thing is going to be 2 times x plus 1 to the 1/2. And again, if you want to go through the full integration by substitution to show that it's a good exercise to do that, the reason I'm skipping is because if you go through and do that and assign u, right, if u equals x plus 1, I have to call it h of x here, h prime equals 1, so when you multiply it out, you don't pay any attention to it in the slightest. When you change variables, rather. The d changing from dx to du has no effect in the slightest because the derivative of that h prime, that h there, is 1. Right? A little slower, if u equals x plus 1, then du is going to equal h prime dx, but h prime is 1, so du equals dx, and therefore changing variables has no effect on anything in the integral. The upshot being we can actually figure out this integral as is. Now we go back, and we have to integrate this thing. So by parts says this integral is equal to f times g minus the integral of f prime g dx. Fg is 2x times x plus 1 to the 1/2. This integral here, f prime is 1, so that goes away. You get 2 times x plus 1 to the 1/2 dx. Again, that integral has an easy form, even though it looks confusing and complicated. The substitution is easy because if this is your h prime is 1, so changing variables changes nothing. This thing down here, writing it all out again, because I have some more room to do this, is 2 times the integral of u du, u to the 1/2 du. I just changed variables from x plus 1 to u. And then I can go through and finish this off. The integral of u to the 1/2, you add 1 to the exponent. That's 1/2 plus 1 is 3/2. You multiply by 1 over 3/2. That's 2/3. So you get 2 times 2/3 times u to the 3/2 plus c. And if you want to, you can, well, you should go back and at the very end, minus 4/3 x plus 1 to the 3/2. Replace back the x for the u. And that's it. We've just done a reasonably messy looking integral. It took only a few lines using, well, a couple of the rules put together. And that's it. So that's how you use integration by parts. In the very last module, we'll put this all together briefly and talk a little bit about how to deal with more complicated integrals. Although, unlike for derivatives, because a lot of more complicated integrals can't actually be integrated, we won't go into too much detail about how to deal with really complicated ones. We'll just give you a sense of how to understand when to use what and how to approach integrals in general. Thank you very much.